Welcome you all in this session of fluid machines. In the earlier classes, we have learnt about the hydraulic turbines. We have learnt impulse turbine, that is Pelton wheel turbine. We have learnt radial flow reaction turbines, for example, the Francis turbine, and also the axial flow reaction turbines, that is Kaplan turbine. Now we will study an important parameter as far as the turbines are concerned, that is the specific speed of a turbine. First of all, we will define the specific speed, we will derive an expression for the specific speed, then we will analyze it physically, that is we will understand the physical meaning of the specific speed. So let's derive an expression for this for the specific speed of the turbine. So first of all, I will define the specific speed, then I will derive an expression for the specific speed of a turbine. Please note, the specific speed of a turbine is defined as the speed of a geometrically similar turbine, which would produce unit power, when working under unit head. So this is a simple definition of a specific speed, that is the specific speed of a turbine is defined as the speed of a geometrically similar turbine which would be producing unit power while working under unit head. So this is the basic definition of specific speed. Now let us derive an expression for the specific speed using this particular definition. Please, since we know that the overall efficiency of the turbine is given by the expression P upon rho g q h. Note, this is the shaft power. Please note, this is the shaft power. This is the water power. This is the water power given by the expression m dot gh. I've used m dot has been replaced by rho multiplied by discharge. Rho multiplied by discharge is the m dot. So this is the expression for the overall efficiency of the turbine. Now power can be written as directly proportional to rho GQH. Power can be written as rho GQH. Now since hydraulic machines deal with the incompressible fluids like water, so rho is a constant and the acceleration due to gravity usually do not change. So taking the acceleration due to gravity as constant, we have P is directly proportional to discharge multiplied by head. Now please note one or two points. Since Q is given by area multiplied by velocity, for example, so Q is directly proportional to area. Area is d square. Area can be written as d square. Area is proportional to d square and the velocity is proportional to root h. From where we have seen the velocity Vf is proportional to root h. This velocity is proportional to root h. So Q is directly proportional to d square root h. So Q can, putting the value Q over here, proportional to d square root h. So it becomes d square h raised to power 3 by 2. Please note, I have used simple expressions. Q is equals to area multiplied by velocity. Since discharge area is directly proportional to d square and velocity is directly proportional to root h. Please note, flow velocity Vf, I have given you an expression flow velocity Vf. The flow ratio is given by Vf1 upon root of 2gh. The flow ratio. So this Vf would be directly proportional to root of h. Therefore, the velocity is directly proportional to root of h. So I have used this expression over here. P is directly proportional to d square h raised to power 3 by 2. Now we know that. Again, I am using one more expression. U is equals to pi dn over 60. U is equals to pi dn over 60. And this U is equals to pi dn over 60. And U is directly proportional to root of h as well. How? I have given you an expression for speed ratio. Since K is equals to U1 upon root of 2gh. Therefore, U would be directly proportional to root of h. So U is directly proportional to root of h, which is equals to pi dn over 60. From this expression, we have dn is directly proportional to root of h. Dn directly proportional to root of h. Therefore, D is directly proportional to root of H by N, and therefore D square is proportional to H upon N square. Now put this value over here. We will have P is equals to, P directly proportional to H upon N square, H upon N square, H raised to power 3 by 2. Clear? Please note directly proportional to H upon N square, which implies further that let me write. Please observe. We have done. So P is directly proportional to H raised to power 3 by 2 plus 1, that is 5 by 2 over N square. 5 by 2 over N square. Now let me use the boundary conditions H which were specified in the defining the specific speed, which would produce unit power when working under unit head. It is the speed of a geometrically similar turbine which would produce unit power while working under unit head. So first of all, let me take P equals to some constant K N square. Now putting when P is equals to 1, H equals to 1, unity. I'm not using their units. When P equals to 1, H equals to 1, then the speed N would be equal to specific speed Ns. Specific speed is denoted by Ns. So please observe, when P is unity, H is unity, then the speed at which the turbine is operating is the specific speed. So I have put over here, I have to put over P equals to 1, H equals to 1 and N equal to Ns. This is from the definition. It is the speed of a geometrically similar turbine working under unit head and producing unit power. So I am taking power equals to unity, head equals to unity, then speed of the turbine would correspond to the specific speed Ns. Please note. So P equals to 1, K, H equals to 1, then N would be equal to Ns. So from here, Ns square comes out to equals to K. Now put this value of K in this expression. We will have P equals to Ns square H raised to power 5 by 2 divided by N square. From here, Ns comes out to be, Ns square is P N square upon H raised to power 5 by 2, or Ns can be written as N root P over H raised to power 5 by 4. This is the expression for the specific speed. This is the simple expression for the specific speed. What I have done, I think we have done to this point. Now, as per the definition of specific speed, when head is uniting, the turbine is working under unit head, producing unit power, then the speed corresponds to the specific speed. I have imposed these boundary conditions into this expression. P equals to 1, H equals to 1, then N corresponds to Ns, that is the specific speed. From here, constant comes out to equal to Ns square, and from here the specific speed has been calculated. This is the expression for the specific speed of the turbine. Now observe 2 or 3 important points. First of all, this is not a dimensionless term. This is not a dimensionless term. Some of the authors may confuse you that this is a dimensionless term. Please, this is not a dimensionless term. Rather, it has dimension. It is a dimensional term. It is a dimensional term. It is a dimensional term having dimensions, having dimension. Please note. Some of the authors may confuse you that specific speed is a dimensionless term. No, it is not a dimensionless term. Rather, it is a dimensional term, and it is having dimension. It is having dimension f 1 by 2, l minus 3 by 4, minus 3 by 4, and T minus 3 by 2 and T minus 3 by 2. Here F corresponds for the force Newton. So this is the dimension of a specific speed ns, and this ns n root p upon h raised to the 5 by 4 is not a dimensionless term. Please note, some of the authors may confuse you that this is a dimensionless term. The specific speed is not a dimensionless term. It is having dimension this for turbine. Please now note one more point. Usually when specific speed is written in numerical digits, for example 100, then units are not mentioned. The units are not mentioned as a convention. As a convention, the unit is not mentioned with the specific speed. It is written like this. For example, units are not mentioned. Units are not mentioned as a convention. As a convention. That is why the authors may confuse you. That is a dimensionless term. Units are not mentioned as a convention. For example, ns is 100. Simply we write units. We do not write what is its unit. For example, ns equals to 100 units. Specific speed is 100 units. So its unit is not mentioned. Unit corresponding to this dimension is not mentioned as a convention. So specific speed is a dimensional term. It is not a dimensionless term. It is a dimensional term, but its unit, when writing in numerical form, its unit is not mentioned as a convention. As a convention, its units are not mentioned. Now please note about this expression. Please note, if you are putting power in kilowatts, if P is in kilowatts, you have to put P in kilowatts and H in meter, if P in kilowatt, H in meter, then you will have specific speed this much units. This is SI units. In SI units, you have to put power in kilowatt and head in meter. Then you will have specific speed in SI units. If you are having power in horsepower and head in meters, then specific speed, whatever the units are there, it would be in MKS units, MKS system. Please observe. So whenever we are writing specific speed, we have to write like this, but whether it is SI units or in MKS units, we have to accordingly put the value of power and head. So in generally we deal with the SI units, therefore we have to put power in kilowatt in this expression, we have to put power in kilowatt in this expression and H in meter in this expression to get the specific speed in SI system of units. Please note, if power is in kilowatt, H is in meter, then unit of the specific speed would be in SI units. And when power is in HP and head in meters, then specific speed would be in MKS units. So this is the specific speed. It is a dimensional term given by this parameter. Please note. Now, please note 2 or 3 points over here. The formula of the specific speed is independent of the diameter of the runner. Please note 2 or 3 points over here. First point, very important pump. Sorry, let me first write expression for the specific speed and root P over H raised to power 5 by 4. Now the first important point which you can notice from here is, for a given power and head, turbine with low specific speed have low RPM. Please note, for a given power and head, if the power and head are given, then the turbine with low specific speed would have low RPM. And as the specific speed increases, the RPM of the turbine also increases. Please note, for a given P and H, the turbine with low specific speed runs slower, that is having low RPM, and is in RPM over here. So for a given power and head, the turbine with a low specific speed will run slower, and the turbine with a higher specific speed will run faster. and as speed n increases directly with the specific speed. Clear to you? For a given power and head, the turbine with low specific speed will run slower, means it would have low RPM, and a turbine with higher specific speed will have higher RPM. So accordingly, according to the application, you can select the turbine. Please note, you can select this, the expression will enable us to select a turbine for NP and H, for combination of NPH. For our combination of NPH, getting the value of NS will enable us to select a turbine. Clear? Second point, since NS is inversely proportional to H power 5 by 4 for a given RPM and power, therefore it can be said that for higher heads, lower specific speed turbines are used. For higher heads, lower specific speed turbines are used. Lower specific speed turbines are used. For higher heads, usually lower specific speed turbines are used. So there are the two important points which enables us to select the turbine. This expression will enable us to select a suitable turbine for our application for combination of these operating parameters N, P and H. These are the operating parameters: speed, power and head. For this combination of the operating parameters, we can select a suitable turbine for our application using the expression of the specific speed. Clear? This is the physical meaning of the specific speed, and this expression is independent of the third point. This expression is independent of diameter of the runner. Therefore, this expression is independent of size of runner. The expression is independent of size of runner or diameter of runner. So this specific speed enables us to select a suitable turbine in a particular shape turbines. In a particular shape turbines, that is in a homologous series of turbines, we can select a suitable turbine for our application. So these are the some important points regarding specific speed, and this is the specific speed. I am again going to tell you that a specific speed is a dimensional term. Having dimension f raised to power 1 by 2, L raised to power minus 3 by 4 and T minus 3 by 2. This is a dimensional term. Now if I can define non-dimensional, I can also define non-dimensional specific speed. Non-dimensional specific speed, which is also known as shape number or shape factor, Here I am defining a non-dimensional specific speed, which is given by shape number or shape factor, and it is nothing, it is simply n root p over rho raised to power 1 by 2 and gh. This is a non-dimensional specific speed. This specific speed is a dimensional specific speed with the dimensions which were written on the previous page. And this is the non-dimensional specific speed, which is also known as the shape number. Okay, thank you.